All right, so is the screen visible for everyone? Hello. Okay, so you can see the screen?
Yes.
Okay, perfect. So is there any question from what we have been covering so far? Whatever we did up until this point. Any question from anyone?
Sir, can you share the lectures and the notes?
Okay, all right. So I'll share the notes. I don't know if at this point they have been uploaded on the website, but they are uploading the notes on the website. So I'll just write over here from where you can get the notes, right? So the notes they're regularly shared on megalecture.com. And once you go there, you can go to the section of, I think it's called Steady Notes. Go under Steady Notes. You're going to see A level something, right? A level physics notes. Under that, you can go to Notes by Basil. That's my name. And once you open this, then you can find A-level notes as well in this section, right? I don't know if this thing is there, but under Steady Notes, you'll scroll down, you'll see Notes by Basil, and the notes are shared over there as well. I'll see. I don't think that these notes might be available as of yet. I'll see, and I'll upload these. I'll ask the management to upload these notes, and you can access them from there. If it takes time, then I'll share these notes in the group as well, right? I'll share all of the notes that we have made so far. I'll try to share these all of them by tomorrow, right, in the group. So is that okay?
Yes, sir.
Okay, perfect. All right. So, okay. So any other question from anyone? All right. So I'll assume that there is no question from anyone at this point. And with that, then we'll continue what we were doing, right? We have started the matter section, and we were doing the topic of ideal gases, right? And we've moved on to the kinetic theory of gases, where our goal was to derive at this point the relationship between the velocity of the molecules to the pressure that is exerted on these molecules. These molecules would be the molecules of an ideal gas. We made some assumptions. We said that there are negligible forces between all the molecules. That means that the molecules, when they're sitting over there, the forces, the interatomic molecular forces are almost zero. However, when the molecules are going to collide, that force is going to exist, which would be the cause of pressure as well, right? And we said that the volume of all the molecules would be so small compared to the volume of the container. The total volume of the molecules would be almost negligible if we compare it to the volume of container. Then we said that all of the collisions that are there between the molecules and the walls of the container, they are completely elastic in nature. Then we said that the time that is spent during the collision that is happening is very small compared to the time that happens between the collisions, right? So this was kind of if it's still if this point is still unclear, you can let me know and we can talk about it. But I tried to explain it last time, and then we said that the molecules would be really identical and they would be moving randomly due to the Brownian motion, right? So that's also a reasonable assumption. All right, so we started off by imagining a container, a box. You can say that it's a cube or something. And so we considered a mole of, or you can say a mass of a gas. Suppose the mass is mass m, and it moves in this container with some velocity v, right? Now the container is of size length L. Every side is length L. All right, now the molecule is moving with speed v. So what would happen in this container is at one point, obviously this molecule is going to collide with a wall, any of the wall of the container. And when it collides with the wall of the container, it's going to rebound with some velocity minus v. And so we found out the change in momentum. So at this point, I'm just revising, so I think I'll go a bit quicker. So we wrote down the expression for the change in momentum. And the reason for that was because we want to write down the expression for force, because when I have the expression for force, then I can quickly write down the expression for the pressure exerted in terms of the velocity, right? Because the force or the momentum is in terms of velocity. So as soon as I found the change in momentum, then all I had to do was to write down the expression for force, which is how fast does my momentum changes. But at that point, we have this delta t, and we can also write this delta t down by considering the distance that a molecule will travel before it collides with the same wall, which I highlighted in yellow. Maybe let's pick this wall. So the distance that this molecule would travel when it collides with it, and then it rebounds, and then it will collide again. So that distance is 2 times the length of the box, right? And so we covered all of this. Why is it like that? And if you don't understand it, you can feel free to stop me and ask me why is it. But we did all of this in the last lecture, and so that's why I'm just going through it. And so that you found an expression for time, which is distance by speed, right? We know that. And so distance is 2L, and speed of the molecule is v. And hence we have the expression for delta t as well now. So we have delta p and delta t. Find the ratio, we get the force, and the force is given as mv squared by L, right? By substituting these expressions for delta p and delta t. All right, so now the next step was to write down the pressure, right? The final thing that you need, really. So we know that pressure exerted by a force, right? A force is necessary to exert some pressure. It is defined as the force that is exerted per unit area. So I'm exerting a force on some area. So that means this point is experiencing some pressure. All right. So the force, we know what is the force, right? We have written it down. It is mv squared over L. What about the area? So let's try this, another dividing symbol. What about the area? What would be the area of this wall that the molecule is going to collide with, right? So this wall that is highlighted in yellow. Anyone from the class, what would be the area of this wall? The hint is that the surface is a cube, right? So what would be the area of this wall?
L squared.
Yeah, exactly. It would be L squared. So it would be the length times length, because this is a cube side, right? So every side is of the same length, which is L. So you get L squared, and then you just rearrange this expression. So this is mv squared. So divided by L squared. So that becomes L cube. And we have more or less at this point figured out the expression for pressure by this one molecule, right? So this one molecule is going to exert a pressure of mv squared by L cube on a wall of this container, on a particular wall of a container, right? So this is just for one molecule. So let's write that down over here. So this expression is for one molecule. All right. So so far, is this clear for everyone? Is there any question from any? Okay, no questions. All right. So that's pressure for one molecule. Now, of course, when you have a gas in this container, right? In this container, if you have a gas, of course, you'll not have one molecule of that gas. In a practical situation, there will be so many molecules of gas in a container, right? So let's say that there are, let me go to the next page. Let's say that this is the container, right? Let me just quickly draw it. We'll have n molecules, right? So we're just assigning it a variable. N can be any value, right? So there will be more than one molecule, at least more than one molecule, right? So the task really is to compute what happens for n number of molecules. So let me write it like this: n number of molecules. How would I write down the expression for pressure if I have n molecules? Okay, so think about this. You might say that the equation for pressure we derived, which was mv squared by what was it? It was 3l squared. It was L cube, right? L cube. All right. There's one more thing over here that we have to, before we go to the case of n molecules, we have to add a factor in this expression to complete this equation, right? For all of the faces, or you can say all of the walls of this container. Because at this point, we have been only talking about a particular wall of the container. So if I consider all of the walls of this container, then I'll have to, when I'm talking about area, I'll have to include for all the walls of the container, and hence I'll add a factor of 3 with this area. Really, this 3 factor is coming from this side, right? L. So let me write it down separately. So the area for all the walls, considering that you have these walls in this container, you're not talking about just one wall. So we'll just multiply this factor of 3 with L squared. So we're considering all of the 6 faces of the cube. So that fixes this expression for all the walls of the container. And so you might now say that if I just multiply this expression with n, then I can have the entire formula for n number of molecules. And to a certain extent, that is correct. That is something that we always do when we need more, when we have more number of molecules, or when you study electricity and magnetism, when you have more turns on the of the solenoid or something, you just multiply the expression with n. But in this case, think about this, that you have these molecules in this container. Not all of these molecules are going to be moving with a particular speed, a fixed speed, because they're going to be colliding with each other, right? So they might, for example, let's consider these 2 molecules. They're going to collide with each other, and when they collide, there might be some loss in speed, right? And then it will collide with something else again, and it will gain more speed. Something might gain speed, some of them might lose some speed. So there will be different variations of speeds of these molecules in the container. So what I need to do is I need an average value for the velocities of the molecules. So is it clear so far? Everyone is understanding, or is anyone lost at this point? Hello?
It's clear.
Okay. Because the molecules will have different velocities. So we need to average out for all the velocities so that we can use a particular velocity, which we can assume that the average velocities of the velocity of all the molecules would be that particular value. This thing is also given a name, really. It's called the mean square of velocities, and it really is just the average value of the square of velocities. So what that means is that let me also write, how do we write it? You write it with this bracket. Let's use v squared and this bracket. All right, now this is known as the mean square of velocities. Sometimes it's also called the expectation value, right? Expectation value for the velocity squared. And it's calculated simply by taking the average of all the velocities. So for example, suppose you have n molecules. So there will be, I'll write a shorthand notation first, and then we'll make it, we'll open that as well. So it will be this thing, Vi, this I goes from 1 to n, Vi squared divided by, you would have over here, this sum would be just over here, and this whole thing is divided by n, right? Which just means that it would be V1 squared plus V2 squared plus V3 squared plus so on, right? So all of the for all of the molecules, we have to add the velocities. So this would be Vn squared divided by n. And this is nothing but the expression to compute the average value, right? So are you familiar with, do you know how do we compute average values? Is this expression understandable, or should I elaborate more on this thing?
Sir,
It's
can you explain once again, how did you get 3L cube in the above formula?
Oh, you mean this, how do I get this factor of 3, right? That's what you're asking? Okay. All right. So if I go back over here and look at this box, now the molecule that we are considering, this molecule, it is always perpendicular because it's inside the box, right? So it's always at a 90-degree angles to two of the faces, right? So for example, if I consider this face, right, its direction of motion is perpendicular to this face, right? Because when it's going to pass right through it. So it's at the path, you can see this vector V is perpendicular to this face, right? So it's, if I draw it something, it will be like this. Now, because of that, it's perpendicular to two of the faces, this one and the one that is opposite to this one, right? Now, when the molecule is sitting inside this container, what happens is it is obviously at one point, it's going to collide with all of the 6 faces or 6 walls of the container. There are in total 6 walls, right? Up, down, right, left, and front and back. So that makes total of 6 walls. Now it's always going to collide with, so for example, if it's moving like this, it's going to collide with only 2 of the walls. So out of 6, it's colliding with 2 of the walls. And if it's moving in this direction, then it's going to collide with this one and this one. If it's moving in up and down direction, then it's going to collide with the top one and the down one. And if it's moving in of the page or outside the page, then it's going to collide with the front face or the back face. So out of 6, it's only really interacting with 2. So we have 6 faces and it's only interacting with 2. So divided by 2, which gives us 3 faces, right? And this is only because they are perpendicular. With the direction of velocity and the area vector of the face, or you can say just the face of the container, these 2 things are perpendicular. Is that clear? I'll take this thing. No. Okay. So if it's not, you can let me know. It doesn't. I'll explain again. No problem. So, but if it's clear, then we'll proceed forward. Okay. So is it clear for everyone in the class?
Sir, I have a question.
Yeah. Yeah.
That the mean values of velocities, we were talking about that, right?
Yeah. Yeah. I'll go through.
How exactly will we figure those out? Because won't there be a lot of particles to deal with?
Sorry, can you please repeat?
Yes, how would we figure out the velocities individually? I mean, there will be a lot of particles, right? So
Oh,
how is
right.
this
That's a very good
applicable?
question, right? Okay, so that's a very good question. Of course, you cannot really figure out all the velocities of all the particles, And that's one of the reasons that we are finding the average value, right? Now, if you're given a question from this thing, you will be given that there are in total, they'll give you the number of particles in a box, right? They'll not give you all of them. They'll say there are 5 particles, right? And what they might do, normally what I see is that they give you a table of values, something like this. So here we have the velocities, here we have n, right? So for example, for particle 1, they'll give you a velocity. For particle 2, they'll give you some velocity. For particle 3, and likewise, right? 5 and 6. So they'll give you some velocity. It could be 2 meters per second. It could be 3 meters per second. And I think you get the point, right? So is that what you're asking?
Yes. Yes. Thank
Yeah.
you.
So it's normally when you're doing a question, it's something like this you can have. Otherwise, if you're talking about how do you experimentally, you can experimentally figure out the velocities of some of the particles, but even that is very hard. And so we find some of the velocities and then we just compute the average. So we can, in general, we can say that this would be the average value, because of course there are, it's not wrong to say that there are infinite number of particles in this box, right? So that assumption is always valid. You can make that assumption, and then you use the tools from statistical mechanics. It's one of the branches of physics, and you can do those calculations. But I mean, of course, they're not the part of this course, so we'll not go into that. All right, so is this clear for everyone? How do we write down the average or the mean square of velocities? And also, by the way, is this also clear that why do I need the mean square of the velocities? Why do I need the mean value of this thing? Is it clear for everyone?
Yes.
Yes, yes.
All right, perfect, good. So, okay, just a second. All right. So now we have this mean square of velocities, right? Now we'll use this average value in pressure instead of using the velocity, right? If I need for n molecules, I need to write down the pressure, then that would simply be n, right? N is the factor that I'm adding. M, right? M, we already had M, and divided by, we had 3 and L cube, right? Now, in place of velocities, I'll just add this, I'll just put the average value of all these velocities squared, right? So if you compare these two expressions now, mv squared by 3L cube, of course, we'll not be having N, so this would not work, right? So you'll be replacing V squared with the average value of all of the velocities of these N molecules or N particles. And so this is the pressure that I would get. Now, what I can do with this is I can make it a bit more neater. How? Well, we know it's very simple actually. What if I have a cube, right? We started with a cube. Now, for a cube, how do I write its volume? What is the volume of a cube whose sides are, all of the sides are L, right? So what would be the volume of this cube?
L cube.
L cube, right? Exactly. So all I'll do is I'll replace this L cube with the volume of the container. Now, this expression becomes 1 by 3 n m v cube, v squared expectation value, or the average value, or the mean square value, divided by v, which is the volume of the container. Now, and by the way, sometimes I might call this thing the expectation value of v square. Understand that I'm just talking about the average or the mean square value, right? That's why I told you it's also sometimes called the expectation value. I work in quantum mechanics, and over there we always call the average value expectation value, and so I might be used to that word. So you'll have to, hopefully you'll understand what I'm talking about, right? Yeah.
Sir, volume you just replaced with L cube, right? So, okay, sir, you can continue. I will ask afterwards.
Okay, yeah, no, you can ask right now. It's okay. If it's something lengthy or something, or if you think that you don't want to ask right now, then you can just text me on WhatsApp as well, right?
Yes.
So it's up to you. It's up to you. Okay, so now you might be thinking, wow, what a step that we did by just replacing L cube with V, right? But it's an important step, because not every time we'd be talking about a cube, right? It could be any container, might have any geometry. So this would be the volume of that geometry, right? Now, normally you'd be finding that geometry to be a cube in your course, but when you do physics later on, and when you obviously you can have containers of different shapes, right? So the volume would be of that particular shape, right? Of that particular geometry. So now you can rearrange this expression a bit more by comparing it with the equation of state. And we all know now that the equation of state for the ideal gas is PV equals nRT, right? So if I rearrange this expression to make it a bit like this, then I can write this expression as P times V by taking that V over there, and I'll have 1/3 Nm expectation value of V squared, right? So that's this expression can be now compared to the equation of state, and then you might write something as 1/3 Nm expectation value of V squared equals nRT, right? So this thing is what we'll be using actually to write down the relation of how temperature is related to the velocity of the particle. So we all know, I hope you all know now, we all already know that when you increase the temperature, the molecules start jiggling more, right? They start vibrating more. They start to basically, it increases the velocities of the particle, and that's what heat does, really. So increasing the temperature, increase the velocity. And so we'll see now the next step really, in fact, is to see how does temperature relates with the molecular kinetic energy of a particle, right? But before we go on to that, let's do a small example that would cover this equation that we derived. This equation is worth of boxing, really. So I'll just box this equation as P equals 1/3. What do we have? Nm expectation value of velocity squared divided by the volume, right? So we'll just box this expression. So what this expression is telling you, it's telling you that if the particle's velocity is higher, or the average velocity of all the particles, n of these particles combined, is increasing, that would produce a higher pressure or a greater pressure on the walls of the container. That's why if you heat, if you might have experienced this thing, if you heat something so and you know, maybe you can even put a glass, and if this is heated so much, the glass might, you know, if it's covered from the top, it might explode, right? And that's simply because you're heating it, you're increasing the velocity of the particles inside this glass, and so they collide so hardly that the pressure, they build up to that particular pressure where it's enough to break the glass, right? Okay, so by the way, before I do the problem, is everything clear? From all of this?
Again?
Sir, can you explain it one more time? The formula, how did you drive it?
You want me to explain this expression for pressure?
Yes, sir.
Okay, I'll quickly go through this topic once more. Okay, so of course, I'll not go into these again, all these assumptions. We really made some of the assumptions before we started off deriving this relationship. Then we really considered, we started off really by considering a gas molecule of mass m in this cubic box whose side is length L, right? And we say that this molecule is traveling with some speed or velocity v, and this molecule travels in a parallel direction in the box, parallel to these side L, right? This one. So what happens is when it's traveling inside there, it's going to collide with one of the walls of the container, and then it will rebound or recoil backwards. When it collides with the wall, it's going to move backwards with the opposite velocity, right? So minus v, really. And so if that happens, then of course there is a change in momentum happening, and then change in momenta can be calculated using the P2 minus P1. This negative sign, extra negative sign appears over here because the velocity is the rebounded velocity, which is in the left direction, which is given the sign negative. And that's why we have change in momentum is minus 2mv. Now, once you have this change in momentum, the next thing we see is that if I can look at this molecule over here again, it's going to travel a distance of 2L before it hits this wall over again, right? So it's going to come to this wall, it hits this wall, and then once it hit it, it's going to travel back. So it's going to cover a distance of L. Now again, it's going to come and hit this wall, so it will cover a distance of total 2L, right? L plus L, so that's 2L. So that's why the distance is 2L, and the time that it takes for this collision to happen with the wall is distance divided by the speed of the molecule, and the distance is 2L, the speed is v, right? So that's where we get this expression for time. Now we have this expression for time, we have the change in momentum, so we can easily compute force, which is given as the change in momentum per unit time. So the change in momentum is minus 2mv, time is 2L by v, right? So we just substitute and we get this expression for force. Once you have force, all you have to do really is to write an expression for pressure, divide this force by the area of the wall that this molecule is going to collide with. Now, the factor of 3 really came from the fact that there are 6 walls, and if the molecule is moving in this direction, which is horizontal, it will only collide with either this wall or it would collide with this wall. Similarly, if it's moving up or down, it's going to only collide with the up wall or the bottom wall, right? So having 6 walls, it's only going to collide with 2 of them. So we'll just divide 6 by 2, and that gives me 3. So when I'm writing the area, because area is associated to the wall, it's going to include this factor of 3 with area, right? 3 times L squared. So that's how we got this expression for pressure. And then moving on, we said that, okay, well, that's good enough for a molecule, one molecule. What about a real scenario, really, where we have more than one molecules, n molecules? So we considered a gas which has more than one molecules, of course. And the problem was over here that all these molecules, they might collide with each other, they might collide with the walls. There will be some change in all of these velocities, right? All the velocities might differ by some value. Now that change has to be accounted for, and we can do that because there's so many molecules, we cannot individually write all their velocities and add the pressures. But what we can do is we can simply find the average value, or which is called the mean square of the velocities, or the expectation value. Once we do that by using expression we know for average values, we can simply replace that velocity with the average value of the velocity and multiply the expression by n, and that gives me the expression for pressure. The rest is just relabeling L cube as the volume and just rearranging some of the expression, and so you get this equation. Over here, I was just comparing it with the equation of state. All right, so is that clear? Umar, is it clear? Do you understand everything? I tried to go through all of this thing quickly, but
Yes, sir, I
hopefully-
get it.
Okay, great. All right. So let's see how much time do we have left. We have 1 minute 27 seconds, and I don't think that we might be able to complete the problem, but let's see. Okay, so let's consider an example so that we can understand the use of this expression, right? So let's suppose that you have a gas, right? Let's suppose that you have just 1 mole of this gas, and it's at room temperature RTP, room temperature and pressure. Room temperature is about 300 kelvins, or it's actually 293, but you can just take it as 300 kelvins. And the pressure is about 1.0 into 10 raised to power 5 in pascals, right? So the gas is maintained at this, and at this temperature and pressure, this gas is going to occupy a volume of 24 decimeter cube. All right. Let's start by first computing the mean square of the velocity of this gas, right? So suppose, first I'm going to suppose that the gas is helium gas, right? Helium gas. So for helium gas, the atomic mass of this gas is